Good morning, good afternoon, or good evening, depending where you are on the globe. We have today more than 350 people registered from virtually every continent, the Americas, of course, Europe, but also Africa and Asia. Dear ladies and gentlemen, it's my utmost pleasure to welcome you here on behalf of EUROBAT to this webinar titled Battery Innovation Roadmap 2030 2.0. My name is Gert Nijlemans. I'm the Director Communications and Stewardship, and I'm not alone here today, obviously. I'm together with Bernard Riegel at my left-hand side here. He's the R&D Director for one of our member companies, Hoppeke. He will not only present a part of the roadmap, but he will also lead the panel discussion, which we're going to have later during the event. Good, we do have a great lineup of EUROBAT speakers, but we also have a keynote speaker from the policy side. So without further ado, I have the pleasure of announcing Mr. Jens Bartolmes, who is the Policy Advisor, Innovation, Research, Digitalization, Competitiveness at the DG Energy in the European Commission. And he will speak on the role of batteries in the green digital transition in Europe. Mr. Bartolmes, the floor is yours. Thank you.
Thank you very much, Gert. Hope the audio is fine. Good. So you already said it. The future that we are facing will be more and more electric. And especially now it has been pushed to speeds that we didn't expect some time ago through the geopolitical situation, which pushes the migration from fossil to electric even faster. The need to have the most efficient batteries that we can get, be it for transport, power, or industrial applications, is growing at an unprecedented pace. And the annual market is estimated currently, and I will come to the numbers a little bit later, but we currently say around 250 billion from 2025 onwards. Now, I've seen your latest roadmap, and maybe the numbers that I'm quoting during my presentation are a little bit on the conservative side, because I see in the scenario that you are actually bringing forward in your soon to be published roadmap are even much higher than what I will present to you now. We have always to see that one of the main drivers, obviously, is the automotive sector, and we are expecting to have around 50 million electric vehicles on the European roads in 2030. That means, and again, this seems to be very conservative, looking at your estimates, that we are going to the terawatt scale of batteries. I have 1.5 terawatt hours. I see in your estimates that this can reach up to 4 times more. And that we are also will have a much larger, but still compared to cars, smaller part of 80 gigawatt hours of stationary batteries that we need for 2030. But this might extremely increase also in the coming years, because a smart grid and the smart energy system we're looking at will, in our opinion, need much more stationary than it's currently projected. And if this is not huge enough, then we have to keep in mind that by 2050, the European entire car fleet of, again, estimated 235 million vehicles should be electric, and the capacity obviously will increase along with it. You might have heard that actually now also there are concrete proposals on the table for completely stopping the combustion engine by 2035. So this will further push this transition. We have to be very careful that we get all our value chains actually to speed also as fast as this transition is happening. Because batteries will be more and more important, but we have learned on the hard way that actually we have to absolutely minimize any kind of critical dependencies of our energy system. And I won't go further into the unprovoked Russian aggression. We all know that. But I mean, this was really a wake-up call on how important it is to have a varied but also very sustainable and homegrown value chain for everything that we have in the energy sector, or at least come close as possible to it. We need a strong competitive manufacturing sector to achieve this. And we need also to ensure that the deployment of the renewables that we are currently envisaging is supported by the technology that we're producing, then also on the battery sector. We want to strengthen our industrial bases with key initiatives, such as the creation, for instance, of the Solar Photovoltaic Industrial Alliances or the Clean Hydrogen Alliances, but also European Raw Materials Alliances. All these alliances will bring the right actors together, we hope, to actually strengthen all these value chains in the fastest and most robust possible way. When we come to outlook, and then again, maybe you have even more recent numbers than we have, but obviously we are very much looking into the competitiveness of European industry and the whole sector. So we are issuing a yearly Commission annual report on competitiveness of clean energy technologies. And I'm happy to say it was actually the 2022 edition was just adopted today. So, and in this report, actually, we see that there's huge progress in the battery technology in the EU, but it shows also that there's so much more to do still. We're on the right track, but we have still to speed up further. And while it was a record year in 2021 for the deployment of stationary batteries and electric vehicles, maybe, hopefully, also thanks to the Green Deal policies, we still need to have one record year after the other to actually meet the expectations there. Repower EU is further pushing variable renewable energy, and this will, as I said also before, increase drastically the need for stationary batteries. And so we might be actually looking easily in the range of hundreds of gigawatts in 2030. So again, big pressure on your sector, but I think a huge opportunity also to stand up to this challenge. These are all figures that are changing almost day by day, because when we just look back 2 years ago, when we published our climate target plan, by then the request for batteries is going skyrocketing. So we couldn't have even foreseen it then, but things are evolving extremely fast. And so most probably these figures that we are talking about now will be corrected upwards very frequently. To meet all these challenges, in October 2017, the European Commission launched the European Battery Alliance to address this huge industrial challenge in a holistic way. And obviously you are part of this, and the European Battery Alliance assures largely to cover the need by homegrown production. That's very important for Europe, and we think we're currently on track because for 2025, it's foreseen that we can cover 69% of battery demand, and then by 2030, up to 89%. Hopefully, we can live up to this challenge. And there's also new battery regulations on the horizon, which is currently in the final stage of the legislative process. And hopefully this will also bring a further push to the sector. We are spending lots of efforts and money also in research. We have a very, probably the world biggest framework for research and innovation. It's called Horizon Europe, for those who don't know. And in this one, we have earmarked close to 1 billion euros for batteries in this financial framework that is actually still running up to 2027. And also their big focus is actually put on making the European battery landscape independent from outside shocks as far as possible. That includes obviously also critical raw materials. So there is a European co-program partnership, BAT for EU, which supports this research in the field of batteries. And it's looking at the whole battery value chain from raw materials down to recycling of batteries in the end. EUROBAT, our host is obviously is part of BEPA and the BAT for Euro partnership. And we are actually really appreciating your input to guiding the R&D agenda for batteries and to help Europe to meet the objectives of the Green Deal on the way. We have also others like the European Innovation Council Accelerator Program, and also they spend close to 150 million already on energy storage projects, of which batteries obviously are a big part. We have something that from the magnitude is even bigger, which is called the Important Projects of European Common Interest. And currently we have two very, very big ones on batteries. They bring together 60 companies, 12 member states, and we're talking here about 6.1 billion in state aid and 15 billion from private sector investment. So you get an idea on how much importance is put on this. And this is not just these two projects. These two projects will help actually to set a landscape of high collaboration in Europe on this technology. So it's going beyond simply funding these kind of projects. We have also more and more focus on the digitalization of the energy system. So we just published some weeks ago the digitalization energy action plan for digitalization of the energy system, which goes along with the Green Deal and our repower. And actually we think to reach the 45% of renewables by 2030 that we are aiming at, we absolutely need to put more focus on a smart management of the whole system. You know perfectly well how important also for batteries it is to have a smart management system, but this applies also to the whole system. And so we think that decarbonization in general, electrification in specific, will need digitalization to make it work. And in order to steer this and what we call the twin energy and digital transition, we adopted this action plan, which gives several pushes in directions where we have to be more aware of cybersecurity of these new smart systems. We have to look into getting the right data and feed this all back or collaborate with R&I sector to make this actually as good as we can in the shortest time. So with this, I would come to the end of my 10 minutes, and hopefully, so just to repeat again, we have to be very, very careful that we are not running from one dependency into the next one. So when developing batteries of the future and the whole battery value chain, we should always very much keep into consideration that we have to avoid critical raw materials that might strangle the whole process. And we have to actually get production, but also the skill and the best talents, if not back, at least then homegrown, build them up in Europe. And quoting our Vice President Šefčovič from some days ago, we need to take another leap from made in Europe to actually invented in Europe and really grow our homegrown battery industry strong and fast. Thank you very much.
Thank you so much, Mr. Bartolmes, for those opening words. I understand that you have a busy schedule this afternoon and cannot make it to the panel discussion, but I would like to take the opportunity, though, maybe to ask you one question. I'm looking at Bernard to see if something came up from the audience.
I checked for the questions, and I would say at this point you have discussed, and the question would be the diversity of Europe's portfolio on raw material import is a very challenging thing. What does it mean for energy storage systems, especially for batteries?
Okay, I can start by maybe less expert than you can give the answer, but one of the things is we have to really diversify the battery chemistries. This has happened, for instance, by putting less and less cobalt in lithium batteries. This kind of stuff we have to be really looking forward to, not just exchanging now something that currently is still maybe easier to get, but that still comes from critical areas of the world. We have to be also equal. We cannot simply try to build our nice world in Europe on the backs of other countries that actually have to give this kind of raw materials. So I think it's really about directly killing the need for this kind of critical raw materials and trying to get from the beginning the right chemistry that won't need this materials. Then we don't run into the critical situation that we might have right now still with some of the chemistries.
Great. Thank you so much, Mr. Barthelmess. We're not going to keep you any longer, and we'd like to thank you for joining our event, and we wish you a very good afternoon and speak soon. Thank you.
Thank you very much. Goodbye.
Bye-bye.
Thank you.
Good, which brings us now to our first EUROBAT speaker, and actually it will be Bernard Riegel who will introduce the first summary, if you like, of the Battery Innovation Roadmap. He will also explain what is the difference with the first edition from 2020. But before going there, we first like to launch the second Slido question, which should pop up on the screen now. Yes, there it is. How do you think the EU industry will be able to meet anticipated increase in battery demand for the next 10 years? And you have a number of options there. And I see the replies are coming in. Yep, still ongoing. Good, thank you. We would like to continue now with the session here. And I would like to give the floor now to Bernard for the summary of the battery roadmap. Thank you.
Thank you very much, Gert, for the introduction, and also a warm welcome from my side. Ladies and gentlemen, at this point, I would like to give you a short overview and a brief introduction to the revised EUROBAT Innovation Roadmap. The Battery Innovation Roadmap 2.0 is an update of the original publication from June 2020 to account the new and latest technology trends and also to consider changes in the European policy objectives. Primarily, the battery regulation, which was released in 2020, it reflects the technology realities and potential of the best available battery technologies and how they can contribute to the European policy objectives. The updated roadmap includes different kinds of aspects. On the one hand, we updated also the innovation potential again for the mainstream technology. In addition, we included now new and upcoming electrochemistry, especially the post-lithium ion and post-lithium systems. Besides this, we fine-tuned and implemented also new end-user application, new aspects with regards to circularity, and also critical raw materials are included. As all of us know, batteries are identified as a key technology and are in the center of the European policy making. The European Green Deal, the battery regulation, and also Fit for 55 represents the key legislative driver for battery innovation. The Green Deal represented or presented in December 2019 is the one main driver for further electrify end-user application to decarbonize the transportation and the energy system. Innovation in battery technology has been recognized as one of the key enablers to make this happen. The battery directive, the battery regulation should further reduce the environmental and life cycle impact on batteries. And sustainable batteries are needed over the whole life cycle. In addition, the battery regulation framework should further reduce the dependency on imported raw materials for batteries, as the raw materials could come, next slide please, could come out of recycled batteries. For the sustainable battery development, raw materials are needed, which are globally equal, distributed in high deposits with the lowest environmental impact. Next slide, please. So the end-user application, in addition, beside of sustainable batteries, are the continuous development for further development. Could we go to the next slide, please? We have identified different kinds of application and grouped them here around the areas of automotive, stationary energy, motive power, mainly logistics and material handling, and motive power, off-road transportation. The list of this application is not exhaustive and other key markets exist. But it has to be said that in each battery technology has a substantial development potential depending on the requirements of the different kind of applications. There is no single electrochemical system or technology which could meet the challenging end-user demands. Next slide, please. If we are looking on the global market, there are many credible sources predicting different kinds of market trends and scenarios. A most likely one in our roadmap is a five-fold growth from 2020 from 645 gigawatt hour to nearly 3.5 terawatt hour in 2030. The share of lithium about 3 terawatt hour in 2030 and for lead about 500 gigawatt hour. Lithium with a double-digit growth year by year until 2030, for lead a constant or a single-digit growth. The lead market will mainly served for the 12-volt auxiliary and SLI systems, followed by the industrial market here, motive power, and also stationary, especially here telecommunication and UPS. For lithium-ion, the main market segment is the electromobility with 85 to 90%, and also followed with a certain share of the electrochemical storage stationary system. It has to be noted at this point that the prediction of the stationary storage market do not consider the European Commission recently announced Repower Europe plan, in response to the market, to the global energy market disruption. If we are looking on the technology, not all of the mainstream technology has the same maturity level, and further R&D is needed for such kind of technology. The further development of the lead technology will be the lead bipolar technology for lithium-ion, mainly the all-solid state, followed by lithium-sulfur and lithium-air. A very promising technology seems to be the sodium room temperature technology. Next slide, please. At this point, I will come to the conclusion and summarize. At the one hand, all battery technology are complementary and all of them has significant development potential. Having different technology has strategic advantages in regard to the availability of raw materials. And developing all battery chemistries will maximize the contribution to meet the zero pollution targets. We have identified high development potential for sure for advanced lithium-ion generation 4 and generation 5 post-lithium system. And we need also new technology which are required, like sodium-ion, especially in the room temperature version. At this point, I come to the end of the introduction of the roadmap, hand over to the next speaker, which go more deeply into certain application and show you the development potential of the different technologies.
Thank you, Bernard, for giving this overview and summary of the roadmap. I'd like to hand over now to our next speaker, which is Christian Rosenkrantz. He is the Vice President, Industry and Government Affairs, EMEA at Clarios, and he will present Area 1, the automotive mobility. However, before doing so, I would like to launch our next poll question, and I'd like to ask the studio to keep it a bit open, a bit longer, so people can vote when they can. Good. So the question is, with 70% electrified automotive powertrains in 2030 and the changing role of the 12-volt board net, what do you consider to be the most important innovation areas to support the transition from SLI? And you can rank here the importance by clicking on the various options. Good. While people can still continue voting, I would like to hand over now to Christian. The floor is yours, Christian. Thank you.
Thanks a lot, Gerd. Good afternoon, ladies and gentlemen. As we heard from the previous speaker, Mr. Bart Holmes, the automotive sector is key to all the decarbonization efforts in the near future. And with that, I would like to go to the first slide in order to give a market outlook, which is going to reflect the penetration of electric powertrains in the total sector of new cars in Europe. So the next slide, please. Thank you. As you can see, by 2030, we are going to experience up to 70% of new vehicles to be electrified by plug-in hybrids or electric vehicles. We see that some European countries are even anticipating the 2035 potential ban of the internal combustion engine faster in 2030 to go to 100% of new sales in electric vehicles. What we also see from an energy storage demand is that the 12-volt power net and all remaining storage devices in the vehicle are going to remain for all platforms necessary. And the remaining 30% is going to be also then using two battery systems, one on 12 volt and of course on 48 volt for mild hybrid solutions. So at the bottom of the slide, you can see that we are going to see at least two batteries per vehicle, of which one is going to be a changing technology, of course, on 12 volt level with different duty cycles, but still needed. And then the high voltage systems with increasing share and demand, which is contributing what we saw from Bernard earlier to the overall growth scenarios. On the next slide, you can see how these different duty cycles and roles are going to manifest itself in a baseline of technology. We see, despite the fact that the high voltage segment with pure traction applications in the automotive sector is going to be the dominant factor for growth in Europe with homegrown battery technology, that still also the low voltage segment is going to contribute to the overall decarbonization effects and efforts. Though declining segment, we can see that up to 8% CO2 savings can be done on micro hybrid technologies with 12 volt technology, and 48 volt technology in mild hybrid bears the advantage of up to 15% CO2 savings in urban driving mode. In general, the role of 12 volt batteries in all technologies is going to change dramatically since we are going to see an auxiliary function, which has on the right of the slide, the predominant duty cycle of keeping all critical consumers up and beat during the off time of the high voltage battery system, and also to fulfill emergency needs in the vehicle. The next slide is going to bring you the pros and cons of each technology a bit deeper, and also the innovation potential, as we heard also from previous speakers, are going to be an opportunity for all battery technologies at hand. You can see The two main technologies in 2030 on 12-volt level for hybrids are for micro hybrids and auxiliary battery systems shown here. The majority in our projection for 2030 is still going to be lead-based technology. We see that lithium-ion has done a tremendous development also on 12-volt level in the last years. The advantages for lithium-ion are clearly the weight advantage, as you can see, also the high charge acceptance and recuperational charging. The high advantages on the lead-acid side are still the reliability as well as affordability. And one element which shouldn't be neglected is what we heard earlier also from both speakers, the resilience in our supply chain, because we have very high established recycling loops that provide us with over 80% of secondary material as of today already in these supply chains. Having said that, the innovation areas for lithium-ion is, of course, to fast catch up on recycling efficiency, also driven by the European battery regulation, having a higher temperature window of usability. And for lead, it is still the remaining development potential, which all companies are working on, of higher recuperational charging and increasing the cycle life. Going on to another 12-volt application on the next slide, thank you so much, is for the sector of the heavy commercial vehicle standby application, also known as hoteling functions, in which trucks are mandatorily switching off their engine in overnight hoteling functions in order to provide the necessary energy demand to the cabin, including all comfort features. We have two main technologies in that segment, also lead batteries as well as lithium-ion batteries. The majority of the application is still on the lead side in 2030 on these low voltage powertrains of 24 volt, mainly driven by the robustness of the product, which has a high resistance in vibration proof since it is mounted to the frame of the vehicle. But also it is a very affordable and still from cost standpoint reasonable technology, since the demand is pretty high during the cycle life of these products to be exchanged multiple times during the commercial vehicle lifetime. However, lithium-ion has, of course, the advantages of very high specific energy content, has high improvement potential on the vibration resistance at frame-mounted activities, and also we could see the cost to come down significantly over the next years with the proliferation of homegrown gigafactories and their product outcomes. So with that, we are switching gears to the high voltage segment on the next slide, which is going to give us an idea on the pure electric traction, which is going to be the fastest and most growing segment until 2030. There is already quite a track record on lithium-ion improvements over the last years, mainly with single to up to double-digit growth in specific energy content over the last 10 years, which is very significant and shows how much the technology has come already to maturity. There is, of course, in each of the different components of the lithium-ion battery still remaining development potential. We saw also from Bernhard's slide that we will see new technologies coming into the market in solid state technology and also post-lithium technologies. And we would like to make you very briefly familiar with the challenges, innovation potentials, and also near future technology roadmaps. Having said that, we see that also Mr. Bartholmes said that we need to reinforce innovations in material research in order to get rid of critical commodities. We see the cathode innovations with nickel-rich materials, getting lower cobalt content, which is both a cost driver as well as from a raw material sourcing standpoint, a commodity which comes from, at least critical supply chains, to put it this way. At the same time, we see also that cathode innovations are going to contain lithium iron phosphate materials, which bears the advantages of even closing the loop and having a regional mining and refining activities with European sourcing. Still challenges on the recycling side, however. The anode material is going to contain what we see already in consumer applications, a higher dopant of silica, which is bringing up specific energy increase. Still also then with morphological chain challenges to be overcome. And of course, if we switch to lithium metal anodes, we will see in combination with solid state that we have then high energy density gain. At the same time, we have challenges with solid state interface boundaries for dendrite growth to be overcome. The electrolyte is subject to a lot of innovation potential in the past for widening the temperature window for both hot ambition or ambient temperatures, as well as cold cranking capability. In the near future, we will see solid state applications with polymer sulfide and oxide based, where we have then also the opportunity to have higher intrinsic safety layers. And the post-lithium-ion technologies, as also shown by Mr. Riegel earlier, have the advantage to switch to new chemistries. Either lithium sulfur or metal oxide systems are going to be penetrating the market. But we see also that there is innovation potential on both of them before we see a serious application from 2030 on. So there is going to come new innovations. We look forward to it, and our member companies in Europe, in the EUROBAT, invest heavily into these technologies. And we encourage, of course, to see the potential in all electrochemistries in the near future. With that, I would like to pass on to the next speaker, Andrea, for the motive power.
Thank you, Christian, for presenting the area 1 of the roadmap. Actually, before moving to the next area, I would like to launch the next Slido question. And I read it on the screen. Do you expect electricity networks in Europe to become less reliable and more power outage to be expected in the coming years? And then you have an option of replies. Please leave the Slido open for a moment so people can respond. Coming in. Looks like there is a belief indeed that's maybe the case. Good. While people can still respond, I would like to hand over now to Holger Ficke from Excite Technologies, and he will present the area 4, stationary energy storage. Holger, please go ahead. Thank you.
Okay, thank you, Gerd, for the nice introduction, and good afternoon, everybody. Batteries in stationary applications are a very traditional use case with a long development history. Of course, applications have changed over time, new applications have been evolved, and also the used battery designs have been changed to adapt the performance to the changed requirements. We see that this technical development is still ongoing, and the used battery technologies has still further potential for innovation and improvement. Next slide, please. If we talk about stationary battery applications, we see a lot of sub-applications. However, we can group it into 2 big groups. One group is battery for backup power, and the second group is batteries for energy storage. In my presentation, I will talk about batteries for backup power, so uninterrupted power supply, UPS, and telecommunication. And on top of that, I will provide an overview about a special and important use case that is batteries in off-grid applications. The area of energy storage application that you see here in light green will be subject of the following presentation. Next slide, please. UPS batteries provide emergency backup power in case of outages or failures of the primary power source that is the main grid. UPS are available in different sizes, and we have here a range from UPS for small computers, homes, hospitals, agriculture, up to big data centers and power plants. We see here the market overview, and the size in 2020 was 15 gigawatt hours. We have 2 battery technology dominating it, lead with valve regulated types, mainly AGM, but still a small amount of flooded and gel. And we have lithium ion batteries, LFP and NMC chemistry, and a little bit difficult to see here in a very small amount, a niche application, still nickel cadmium. We will see that the market will grow with a cumulated annual growth rate of about 5.5%, and that we expect in 2030 a market size of 25 gigawatt hours. You see here already that lithium ion batteries will penetrate stronger into the market and grow stronger than lead acid, and that we expect that the share will change from 2020 90% LED to 72% LED in 2030, and that lithium will ramp up from 10% in 2020 up to 28% in 2030. Of course, here the main market drivers are the increased demand for backup power for new data storage centers. We have extended service for the batteries, further electrification, digitalization, and also emerging virtual power plants. Next slide, please. If we come to the key performance indicators, power density is very important. And here we see a trend towards shorter discharge times at very high power, so 15 minutes down to 5 minutes and even below. Low cost, safety, reliability, and end-of-life management. The requirements for endurance strongly depend on the area where the UPS system is installed and also the geographic region. And this means, depending on the stability of the grid, we can have cycle lifetimes from only a few cycles per year up to almost daily cycles. We see also that here is a new demand arising for more and high temperature robustness. This is not only due to the increase of the usage in hot countries, but also to the general trend that we see higher power consumption, bigger batteries. But on the one hand side, we see not always that the air conditioning climatization systems are adapted. So in general, the batteries in operation are exposed to more higher stress. Neither lead nor lithium is really fulfilling to 100% the requirements that we have. And so both technologies have innovation potentials. For lead, we have to improve the power density, increase the cycle life, also depending on the use case. We need more maintenance-free products. And of course, we have to cope with a high temperature robustness. In terms of lithium, it is needed clearly to reduce the cost, as has been said before. We need to work on the safety that can also contribute to the cost due to logistic cost, but also safety in operation. End-of-life management has been mentioned before. We need to increase here the recycling efficiency. And also lithium is supposed to cope with high temperature robustness. Next slide, please. Moving on now to telecommunication, we see a lot of similarities also to UPS. From the application itself, of course, in this case, the batteries are providing backup power for telecommunication centers in case that the main power source has outages or insufficiencies. In this case, cells and batteries are connected to form 48-volt direct current energy system, which is a preferred setting here for telecommunication applications. We see here the market size in 2020 was 16.4 gigawatt hours. The two dominating technologies, lead acid batteries, AGM and GAIL, and lithium ion batteries, again with LFP and NMC technology. Lead has here a share of 88%, while lithium has a share of 12%. Also, similar like UPS, we see here a growth rate of about 4.3% cumulated growth annual. And so the market will grow in 2030 up to 27 gigawatt hours in volume. Similar also the change in the share. Lithium will penetrate stronger and grow stronger than lead. And it is expected that lead share will decrease a little bit to 74%. And lithium share will grow up to 26% in volume in 2030. Here again, we can see the increased power demand, 5G rollout are the main market drivers. And we have, of course, also the mobile society. So we have an increase of wireless communication. And so there is a demand that we have to install more BTS installations. Next slide, please. Key performance indicators for telecom, also very similar to UPS. We see here energy density as one aspect, low cost, safety, end-of-life management, and of course, reliability. Again, endurance depends on the application itself and also on the geographic region. And we have here cycle life requirements from short to very long times. And we see here also the same trends. We have bigger systems. This development was already seen when we moved from 2G over 3G to 4G, that we need a higher energy, high power consumption. And so also we see the same tendencies that the thermal stress for the batteries is getting bigger and the batteries need to cope with it. Again, none of the technologies is 100% fit. And so less acid in this case has to improve mainly the energy density. Of course, also cycle life, again, depending on the use case. And here also we need to increase in order to reduce OPEX, to use more maintenance-free products. And of course, also high temperature robustness is here a key development subject. For lithium, again, it's mainly the cost reduction. And here the capital cost is still in factor 2 to 3 higher compared with lead. We need to improve safety, end-of-life management, and of course, again, also high temperature robustness. Next slide, please. Now we move on to batteries in off-grid application. I said in the beginning, it's an important use case, and why it is important. According to the information from the German Energy Agency, it is expected that still in 2030, there will be about 1.2 billion people worldwide without direct access to electricity. The majority in Africa, but also partly South America, Middle East, and Southeast Asia. In such areas, remote rural places, small islands isolated from the national grids, and areas which are very difficult to access energy storage and supply using batteries can be a very cost-efficient solution to solve these issues. The main applications for off-grid are energy storage and backup for telecom stations, but we have also additional applications like purification and pumping of water, street lighting, and security systems. The size is ranging of the installations from small households up to commercial and industrial size. Batteries are installed either as standalone solution or in combination with diesel generators and also in combination with renewable energy sources like solar and wind energy. Of course, one of the drivers for the operational cost is a diesel, and thus the usage of the batteries has here a huge potential to reduce the cost in operation. Again, we see here as the two main battery technologies now in use and also forecasted that this will be true in 2030, lead-ion batteries and lithium-ion batteries, and also to a very minor share, we have sodium-based technologies in this application. Next slide, please. The requirements, of course, are a little bit similar then to the applications in on-grid situation for backup power and energy storage. But of course, we have also some significant differences. We see here most of the application are in developing countries, and so the cost is very important here. In general, we see a high energy throughput, and especially in combination with hybrid systems, we see here a demand for higher partial state of charge cycling because it is not always ensured due to the volatility of wind and solar that the batteries are always fully recharged. End of life management, of course, here in these areas also very important as it is not established like in other areas. And we have even partly the situation that the export for wasted batteries is forbidden. Due to several reasons, batteries in these areas are not always installed in battery rooms. And so they are partly exposed to very hard conditions like extreme heat and low temperatures, but also wind and sand. The main areas for improvement are therefore here for lead batteries, again, increase of energy density, improvement of cycle life, and taken into consideration the energy storage situation, we should also consider here that we have to apply different operational strategies and also use, in this case, or consider to use a battery monitoring system. Lithium clearly has to work on cost reduction in this area as the main target, but also do not forget, of course, safety, end of life management, and also further increase the design life to further reduce the operational expenditures. With that, thank you very much for your attention, and I give it back to Gerd.
Thank you so much, Holger, for presenting your area. And before moving to area 4B, I would like to launch our next question for the audience, which is the following. What do you think, is the most important feature of stationary energy storage systems? And you can rank here by importance of clicking. So while people can have a look at that, and please keep the question open. I would like to hand over now to Valentin Rotta. He is the Director of Sales and Business Development at FREYR. So, Valentin, the floor is yours. Thank you.
Great. Thank you very much. Hello, everyone. Let me first of all start by saying it's a pleasure to have the chance to expand further on the category of stationary storage. So let's first maybe start by defining the terms on the next slide of what exactly are we talking about. So here on the slide, you see 3 categories. So residential, commercial, and industrial, as well as utility scale. And the goal there is really to give you a sense of what's the scale and to define some of the terms we are talking about. So residential, usually we are talking about small battery installation at homes. So 1 kilowatt hour, usually 10 to 15 can go as high as like 30 kilowatt hour. So these are really like small scale kilowatt hour, I would say, products. Then you have the commercial and industrial that are typically more installed like at factories, at I would say more like private sites, and these tend to be a few hundred kilowatt hour to a few megawatt hour. So altogether, residential and commercial and industrial are defined as behind the meter, a term you may be familiar with. And then the third bucket, which is what we could refer to as utility scale. So these are the very large projects, megawatt hour to actually gigawatt hour plus. So, and that's what we will refer to as front of the meter. So now that the landscape is set, on the next slide, you will see some orders of magnitude as to how the deployments are looking. So these are actually cumulative deployments per year for 3 regions. So Europe, Middle East and Africa, Asia Pacific, and America. So on the left-hand side of the page. So as you can see, it's not yet factoring in the new repower plans for 2030. As previously said in the session, it's also pretty difficult to forecast, and the past tends to be a very poor predictor of the future, and we tend to see these volumes really going up quickly. Give or take, Europe is about a quarter of the deployments, and the growth in these different buckets is primarily based on the economics, so how competitive storage is, the technical improvements, and obviously how strong the policy making is driving these developments. Then what do we do with those batteries? What's the application, as we say, and how does that impact the typical battery configuration? So in the past few years, there's been a lot of different applications that have been driving the volume. So ancillary services, so that's what typically we call frequency regulation, and a number of other services. Energy shifting, so essentially shifting energy from midday to later in the evening, or from off-peak to peak periods on the grid, and a combination of commercial and residential. As you see over time, so moving from left to right, we move from past to the future. Energy shifting increasingly becomes the key application driving the volume, with residential and commercial staying pretty strong. So how this impacts the duration of the batteries we develop, actually is it tends to move the duration a little bit up. So the duration is broadly between 1 to 4 hours today in the market. On average in Europe, probably about 2 hours, and we see this duration actually increasing over time. And on the next slide, you will see how that impacts also the technology that's being used. So on the left part, you see what has been deployed in the past. So really a combination of technology, lithium, lead, sodium sulfur, and others. You see over time though that lithium ion has gained a bit of a scale effect, and so today represents the majority of the deployments. And on the next chart on this page, you will see actually the different types of chemistry. So if you please press next, you will see like some of the chemistries we've been talking about. So NMC, so nickel, manganese, cobalt, as well as LFP, lithium iron phosphate. So both are today the dominant chemistry in this field of stationary storage for behind the meter and front of the meter. Lithium iron phosphate has been gaining significant traction over the last few years. We will shortly see why. It obviously has, I would say, embedded effects, judging by the fact that it uses different raw materials. What's interesting is we see the batteries for motive and automotive use increasingly diverging from the ones from energy storage, mostly because the latter used to be more of a small byproduct of the larger EV industry. And now energy storage has really come of age. We see the volume that are going into the market really being more significant than before. And so a number of factors like ourselves are starting to develop energy storage specific chemistries. Lithium iron phosphate tends to be very practical for stationary storage. Nickel manganese cobalt is probably going to retain some market share, notably in the high power, high energy density application. And as we see in the second half of the decade, we could see some potential future technologies are arriving. So sodium ion, for example. There, what will be interesting is obviously to see can this innovation in the lab be brought to the market? And there are a lot of other elements around building the supply chain, building the manufacturing capacity to help these new technologies get there. But we do see that lithium ion LFP tends to be really the main force there. On the next slide, please, we'll look at what exactly is a good KPI, so key performance indicator for storage, and how does it influence the innovation area. So a good key performance indicator is what we call the levelized cost of storage. So you may be familiar already with the levelized cost of energy from which it is derived. And essentially what it looks like, it looks like the total cost, so both the upfront cost and the ongoing cost of a storage system, divided by its energy throughput over lifetime, which is essentially a bit like the mileage of the system. And it compounds both the cycle life and the technical performance. And the lower the result you get, the better. So the lower levelized cost of storage usually points to a more competitive batteries. And it drives innovation areas in a number of different ways, looking into the future. A number of the action are actually working on the numerator part of this division. So reducing the cost as being a key element. So the cost of the battery upfront. So for example, reduction of the cost per kilowatt hour that we have been seeing over the last few years, reduction of the ongoing cost of the battery. It tends to be a little bit less impactful than the CapEx, but it is still obviously something that matters when we look at the overall levelized cost of storage. So that's really the cost reduction impact. Then you have the other aspect, which is increasing the denominator, and that will be done by improving the performance. So performance is obviously a pretty broad term. Performance could be seen as increasing the cycle life. So there's really been a lot of effort of the industry over the last few years. So we've seen the cycling range increase from 5,000 to 7,000 and to sometimes actually higher total cycle counts, which allow often this large and notably utility scale project to have up to 20-year life cycle warranty. And you have also other aspects of performance, such as the round-trip efficiency, for example, which leads to a higher energy throughput. So these are two, I would say, good way to approach the stationary energy storage topic from a quantitative standpoint. That being said, as all good KPIs, it's not perfect. So there are a number of very important qualitative aspects that are not reflected there. We've mentioned supply chain already. Actually, we start to see that supply chain optionality, notably for homegrown products coming from Europe for the European market, is something that is valued, notably when you have logistic disruptions such as we had during COVID. That's an example of a quality element. You have another one, which is safety, for example, and safety is obviously key. There's been a lot of work being done the last few years to standardize the safety for this domestic, commercial, and utility scale project. So really led by the European and the American industry in particular. And the last element that we start to see, pointing notably in obviously the European battery regulation, is the environmental impact. So it can be the environmental impact upfront, so typically the GHG and CO2 footprint. It can be also obviously the cradle to grave overall impact when we include recycling as well. So all these qualitative aspects are very important, and there will typically be elements that players out there, when they go and procure their products, are going to look at. So that was it in a nutshell. So I will just pause there and give you back the microphone, but thank you all for the attention. And if you have any question, I'm very happy to go through them afterwards.
Thank you so much, Valentin, for presenting your area. Before we actually move to the final EUROBAT speaker, I would also like to launch our last Slido question for the audience, which is, do you believe that the motive power market will be an active contributor to CO2 reduction? So while we keep that open, you can vote. At the same time, I would like to invite our final speaker, which is Andreas Saletti. He's the technical director at MIDAC, and he will present the areas 2 and 3, motive power, logistics, and off-road transportation. Andrea, the floor is yours. Thank you.
Thank you, Jared, and thank you to everybody for being here. So the motive power market covers a wide range of off-road industrial vehicles. If you can move to the next slide, please. The first branch of this area is the material handling and logistics, which are key points for the supply chain management in warehouse, distribution center, and for handling of goods in the industry itself. Inside this subgroup, we can find classic forklift and pallet truck, order pickers, reach trucks, and side loaders. The second area considers all the other off-road applications not included in the previous one, where a battery propulsion is required, or where the requirements in the near future is asking to increase the use of batteries. We are talking about a sweeping machine, construction and demolition machine, golf carts, AGVs, harvesting trolleys, etc. But there are also other kinds of transportation, such as railways, marine, and aviation. Next, please. So currently, the motive power market is dominated by lead-acid batteries with 90% of the total share. The rest is lithium-ion technology, while other applications such as lithium-based batteries are playing a very secondary role. The worldwide motive power market is rated today at 35 gigawatt hour, but it will reach 67 gigawatt hour by 2030. This high market growth will consider the lead-based market with single-digit growth, while the lithium-based technology will reach 49% of the share in 2030. Driver for such an outstanding increasing will be noise and pollution reduction legislation, and will consider the replacement of internal combustion engine type machine with battery propelled one. Keep in mind that nowadays in Europe, roughly 80% of the motive power fleet is battery powered, but in other areas such as the United States and Asia, only 60% of the fleet consider this type of technology. Next one, please. The following table shows a list of the main relevant KPIs for this application. In details, we need high discharge and charge rate, energy content, cycle life, high recyclability, low investment cost, power density, extreme temperature performance, partial state of charge cycling ability, energy efficiency, and low maintenance. The different colors applied to the slide indicates which technology between lead and lithium is more strong in the mentioned KPI. Next one, please. If we look at the innovation potential of these two technologies, we can consider for lead acid batteries the increasing of cycle life, the reduction of charging time, maintenance-free attitude, and the increasing of digitalization through the application of Internet of Things. On the other side, for lithium, we have to take into account the reduction of cost, the increasing of safety, standardization, and recycling. Next one, please. The off-road transportation, so we are moving to the other area of the roadmap, cover a wide range of applications that cannot be addressed in the previous area that we already considered. So we are talking about sweeping machine and cleaning machine used, for instance, in factories and mall or in the supermarkets. We take into account wheelchairs to assist people with disabilities or the elderly. The construction and demolition machine like mini loader and scissor lift, a golf cart for leisure and light human transportation, and automated guided vehicles used in the logistics centers. The main key points are derived from the motive power batteries already discussed in the slides before. And the market share for this segment will reach 3.3 gigawatt hours between the 2030s. In this type of market where the initial investment is low, lead acid batteries are dominant, but the need of a higher load, outstanding fast charging, use of partial state of charge, and operation in the area where hydrogen emission or spillage are not allowed will increase the use of lithium-ion technology. Furthermore, lithium-ion technology is likely to become dominant in the demolition and construction business in replacing the internal combustion engine. Next one, please. Thanks. So the off-road, the remaining area to be discussed are all the other off-road applications such as railways, marine, and aviation. So for railway, the current application for rolling stock, such as emergency lighting and power supplies or auxiliary service and cranking of this engine, are well distributed between lead and nickel-based batteries, while lithium is covering a minor area. Since a large part of line operating at low speed or low mileage, all of them are still using diesel engine, so there is a huge potential for electrification and hybridization of this type of vehicles. In this case, lithium technology will cover the 100% of this segment. The marine sector is a strong contributor in terms of pollution, and batteries will become enablers to contribute to the transformation of marine vehicles. This is actually an urgent need, and there is an urgent need of electrification and hybridization of this type of powertrains, but also to increase the use of battery in other applications such as onboard auxiliary services. Propulsion of the large-scale ship will be in the future 100% lithium. Smaller boat will be have also some. There will be also some space for lead acid technologies, especially when we consider the 48-volt hybrid system. And auxiliary onboard system will be split between lead and lithium, while the nickel-based battery will cover a niche market. If you talk about aviation, so according to the International Energy Agency, the aviation industry produces over 1 billion tons of CO2 per year. But the current technologies does not enough energy density for propulsion the commercial aircraft. So the hybridization and development of electric vertical takeoff and landing vehicle is the first step to reduce emission. It is predicted that by 2050, 160,000 eVTOL will fly worldwide and will be powered basically by lithium-ion batteries. About the auxiliary batteries, the scenario is very similar to the one we already see in the railway segment. So where lead and nickel are the main technologies, but the transition to lithium has started. That's all. Thank you to everyone.
Thank you so much, Andrea, for sharing these insights. Now, conscious of time, we're going to move to the last phase within our program today, which is actually the panel discussion. So what I suggest is that we start with some questions, beginning with the area of automotive mobility. So that would be some questions, I guess, Bernard, for Christian Rosenkrantz. The floor is yours. Thank you.
Thank you very much, Gert. And I will, forward first question to Christian. Christian, especially you mentioned the 12-volt automotive market will still be dominated until 2030. What kind of innovation you see and what kind of developments you will do to reach, I think, the requirement until 2030? Or do you think we can stay with the current state of development?
Excellent question. And if I may combine, Bernard, I would even take the first question highest ranked with the innovations in the panel for 12-volt lead batteries. There is still remaining development potential in all electrochemistries presented. Also, lead, as one of the oldest technologies in the market, has development potential. It's mainly around charge acceptance, dynamic charge acceptance, quick rechargeability. Also, in the new applications of an auxiliary powertrain, there is the demand for fast charge acceptance in order to recharge the battery when electricity is cheap in a vehicle, available in abundance, and can be recuperated into the battery system. Zooming out, besides just the activities we do in an individual company basis, Clarios, I would like to highlight that even in an industry consensus, we are working on pre-competitive research with the Consortium for Battery Innovation, which is funding then specific research areas in order to improve lead batteries in the future. So just to give a quick overview, handing it back to you, Bernard.
Thank you very much, Christian. And then I would go ahead, Holger. I think we are going over to the stationary area, and you have also presented for the different kind of stationary applications, the potential of the different technology. In one of the applications you mentioned with small market share, perhaps in 2030, the sodium-ion technology. And the question would be here, why you see only such small portion? If we are depending on raw materials, do you think this could be much higher in the future? What will be the expectations?
Yeah, I think, Bernard, we have to clarify a little bit. What is nowadays in use is, of course, high temperature sodium sulfur. And of course, I think, as you have presented in your roadmap, if the room temperature sodium ion technology will be established over the years, it can be a very good fit because it solves many issues related to safety. And also, I think it covers very perfectly one issue with the supply chain. So the material itself is well distributed. And so this would be a big step forward and could be a good fit for this application.
Thank you very much for this answer. I would go ahead also to the large energy storage systems. There was one question which was considered and discussed a lot of times. What is your expectation for the large energy storage systems to implement the second life batteries out of automotive application? And what will be, in your opinion, the share perhaps if you compare it to new battery systems installation and perhaps outcome of second life batteries?
Yeah. Thank you for the question. It's an interesting one, and I think the answer is multifaceted, so it's not going to be a yes or a no. Just I think a few thoughts. The market already has installed and is operating a second life battery used for battery energy storage systems. So obviously it has great advantages in terms of reusing batteries that were already around. That being said, what we've seen is very often the cycling profile of batteries for EVs and for ESS is quite different, right? An EV usually cycles about 1,000 times. An ESS is expected to do 7,000 cycles over its lifetime. So it does come sometimes with, I would say, that might not cater perfectly with what the ESS application need. The other thing we see is there is obviously a volume component of it. The growth of ESS is really booming right now. So the volumes are really getting significant. There is not enough second life battery to meet this demand, far from it. So I do believe that we will see definitely some second life batteries reused, notably for low cycling ESS applications. That being said, for the large ones, it's primarily going to be new products. Also because I would say, taking a bit of a laptop analogy, those systems usually have 5, 10, 15, 20 years lifetime. And so in 10, 15 years lifetime, the cycle life of new batteries compared to that of today will be materially better, right? So it would be a bit like we're using today a cell phone from 2005. Probably most people would like to recycle the components and get a new high performance product. The last note I would make maybe is also from a financing standpoint and an insurance standpoint. Most of these projects are project finance, or notably when they are co-located with renewables and when they are standalone doing market participation. And so the lenders as well as the insurers, they want to have some certainty about the safety and the quality of the warranty wrap. And they tend to feel a bit more comfortable with a new build product than with second life. So not to say it's not going to happen, but we're probably going to see both and largely primary new build battery in the future.
Thank you very much. Now I think we have another important segment is the motive power area. Going over to Andrea, you have shown the diversity of this market, different kind of vehicles. And we know for Europe and the US mainly, the market for material handling is mainly electrified with 70 to up to 80% nearly. What do you think? What are the requirements to perhaps overcome this issue and also electrify the rest of the 20% of such kind of vehicles?
Thank you for the question. Let's say that first of all, we have to consider that this 80% mentioned is a really high value if compared to other continents, but probably this value is really close to reach an asymptote. So it's going to the maximum value available. But anyway, I think that having a different range of technology available that can cover a wide range of applications, or as highest as possible, will increase and push up this number as well.
Andrea, and I think we can go over again to the automotive area. So Christian, for you, if we stay at the largest market, I think for the lead-acid batteries, the 12-volt market, we discuss a lot. Now you have also shown us that there is a lot of development potential even for the lead-acid batteries. But besides this, what kind of technology could compete in such kind of segment with the lead-acid technology?
Well, I guess the strongest competitor is at the same time one of the technologies with the highest complementary skills to lead acid, which is lithium-ion. There is clearly also an opportunity to use lithium-ion batteries in a 12-volt application. However, the advantage of having multiple electrochemistries is, of course, redundancy and the elements also of functional safety coming along with combining different electrochemistries. But clearly also lithium-ion in low voltage application can provide, of course, a lot of value in 12-volt applications. Having said that, we need to look holistically at all functions. As mentioned in previous speakers, it's really a closed loop in supply and demand, in raw material supply and recycling efficiency, and also in capacity needed in order to decarbonize the entire transportation sector. So I guess we will need all hands on deck is the message.
Thank you very much, Christian. And going back, I think, to the stationary market, to Holger, if we are looking at our innovation roadmap, we were considering different kind of applications, different kind of requirements of each application. Do you see also differences perhaps in the telecommunication area if we are going outside for Europe in other countries, that the application and requirements are changing somehow?
Yeah, I think it's a very good question, Bernhard. We will see this differences in the different geographic areas, and it is mainly related to the stability of the grids. That means the number of power outage and the duration of power outage might be completely different if we go from one area to the other. And we see it even within Europe. If we look from country to country, that there is still a huge difference. And I think this is also an opportunity, let's say, to customize a battery that is fit for the application in certain areas. So always higher, more cycles, higher energy density and so on. This is maybe not even always required. So it gives potential to customize the batteries, the application, and it gives to the end customer a good choice to select among all the existing battery technologies and to choose the one that is giving the best benefit to him.
Thank you very much, Holger. It shows, I think, that we have always different kind of development potential depending also to the end user requirements. And coming to the point, I think, going over to the large-scale energy storage system, Mike, perhaps you can answer us, especially for Europe. What are, I think, the most or the large energy storage system, what they have to fulfill, what kind of requirements in the application? Are there specific fields where the major market share are in Europe?
Yeah, so the large scale storage application, the main requirement for that is really that they store the energy that is coming from renewable areas, so that they really help converting the grid we have today into a more renewable area. So that is really the main idea of having large scale energy storage applications. And here one of the main features really is to be safe, to be reliable, to be low cost. So it's really a lot of requirements to these areas. And that also defines a little bit the difference to automotive area, where you have, especially concerning the lifetime and the cycling, massive differences. As Valentin just mentioned, we are talking in automotive about 1,000 cycles, and in energy storage about 7,000 to 10,000 cycles. So it's really a completely different area, different demand for that. And that area is growing very fast, and we see that more and more requests are coming in for these areas.
Thank you very much. Holger, perhaps a last question, the final one, sorry. We have spoken a lot of the development potential of the electrochemistries. What do you think, what have we done in concerning battery management system, which are required for lithium ion? But do you see that we have also do for other technologies also the same effort to develop them further in the future?
Yeah, well, we have seen on some examples that a good battery managing system can give a benefit. Just to name the M5BAT project, where different battery technologies have been combined. And I think that could be a way forward, especially if it comes to energy storage applications and we have large strings combined of batteries or cells. It could have a benefit if we have more control over the charging and also over the discharging conditions in order to avoid that single cells are drifting. And in my opinion, it is also helpful that we can reduce the overcharge condition, which will give us a little bit more benefit in terms of reduced corrosion, and so will contribute to elongate also the battery life. So I think a BMS can contribute here and improve the battery performance of lead-acid batteries well.
Thank you very much, Holger. I'm sorry, we have a lot of other questions, but we are running out of time, Gert, I think.
Yeah, exactly. And actually, we will also share the list of questions together when we send the follow-up email in a couple of days. So thank you again also to Bernard and the colleague speakers of EUROBAT for contributing to this session today. But of course also thank you to the audience for joining us today, and I hope that you did find it indeed very interesting. And as I mentioned before, within the end of this week, we will follow up with an email containing a link to the recorded presentation for the ones that in the end could not join. But it will also include the documents, both roadmap documents, as well as the slide deck and the questions, as I just mentioned. So before you go, I would like to kindly ask you to give your opinion on today's event. So don't close the browser yet, but once our session finishes, there will be an automatic survey popping up. It will literally take you 30 seconds to fill that out. So hopefully you can also contribute to that. Great. I hope to see you at a future occasion, be it in real life or virtually. And wherever you are, have a nice remainder of the day. Take care and bye-bye. Thank you.